Hey guys, so we're going to start with the Chapter 6 material for your exam. This video is going to cover air masses, thunderstorms, and tornadoes. So first we'll start with air masses. Air masses are classified based on two factors, their temperature and their humidity. Air masses are present all over the world, but in this class we're going to concern ourselves only with the four major air masses that specifically affect North America. So first we have the cold polar air mass, which as the name implies, it originates near the pole and it's extremely cold. We don't really experience its effects too often down here in our part of the country, except in very rare situations. But where Dr. Trepanier is from, Wisconsin, they experience this constantly every winter. It's why the winters are so cold and miserable there, because this air mass is constantly moving into the northern part of our country. So the cold polar air mass is extremely cold. It brings that dry, very frigid air from Canada down into other parts of Canada and our country. So second, we have the maritime polar air mass. So these air masses originate in the northern parts of both the Pacific and the Atlantic Oceans, and they move very wet, cold air inland. This mainly affects Alaska, the Pacific Northwest, and the Northeast. And this is part of why those areas have such nasty blizzards during the winter, because this air mass is moving that air inland and it creates blizzard and snowstorm conditions. So our third type of air mass is the one that we are by far the most familiar with here in Louisiana and the Gulf Coast. It's the maritime tropical air mass. And there are two of these that influence North America, but the one that's very close to us in Louisiana is much stronger than the one in the Pacific. So the maritime tropical air mass that we're familiar with, it's very consistent and strong from the late spring where we are now all the way through the fall. And it's part of why the Midwest has such bad tornadoes. As that air mass moves inland and combines with polar air masses, it creates very unstable tornadic conditions, and it's why we get such consistent heavy rain throughout the spring and the summer here, because that maritime tropical air mass is constantly pushing very hot, humid air inland, and it creates the perfect conditions for thunderstorms to form here. And our final air mass type is called the continental tropical air mass, and it can form only in the summer from inland heating, when the high temperatures here make the land really, really hot. And this air mass brings hot, very dry air into different regions, and it can create some very impressive thunderstorms. We don't experience this too much in Louisiana, but it's a huge factor in the southwest part of our country. And it's part of why California has such bad wildfires in the summer and fall, because this air mass is bringing very powerful winds towards the coast, and it fuels the spread of the wildfires. So to recap our four types of air masses, first we have the cold polar air mass, which is very cold and dry air. Second, we have the maritime polar air mass, which is relatively humid but also very cold air. Third, we have the maritime tropical air mass, which is very hot and very humid air. And last, we have the continental tropical air mass, which is very hot but very dry air. And an important concept to understand about this is called air mass modification. And basically all that is that as these air masses migrate over land, their characteristics will slowly change based on the surface characteristics of the land that it's moving over. So for example, if we have a maritime tropical air mass that starts in the Gulf during the summer and moves northward into North America, over time, as it's cut off from its fuel source, that air will lose some of its humidity through rain, and it will also get colder as it gradually moves to lower and lower temperatures northward. So its effects will be much more powerful here in Louisiana than they will higher up in Missouri and the northern parts of our country. And the same applies to those cold polar air masses that move southward. So they're at their coldest in Minnesota and Wisconsin. By the time they reach all the way down here, if they even do, they've warmed up significantly over the land. And that's part of why we almost never get real snow here in South Louisiana, because by the time those air masses that bring snow to the rest of the country get down here, they've warmed up to the point where the conditions in the clouds are no longer proper for true snow to form in those frozen clouds. We tend to get very nasty sleet, not quite fully frozen stuff down here because of that reason. So we've briefly covered air masses. Now we'll talk about thunderstorms. So thunderstorms derive their energy from two main factors. First, the solar heating of the Earth's surface. The more solar heating there is, the more fuel that thunderstorm will have, and that's why we tend to have a lot more during the summer when the subsolar point is closest to us. And the second factor that fuels a thunderstorm is the condensation of water vapor in the atmosphere. If the conditions are not right for that to happen, a thunderstorm is not going to be able to form properly. But if they are proper for condensation to happen in the atmosphere, then you can get some very powerful storms really quickly. And obviously an extreme example of that is a hurricane, which we'll talk about later. So again, the two energy sources for a thunderstorm are the solar heating of the Earth's surface and the condensation of water vapor in the atmosphere. So globally, thunderstorms are most frequent in the tropics over land. And in the United States, the southeastern part of the country where we are has the highest frequency of thunderstorms because of that maritime tropical air mass we talked about earlier. And the state of Florida has the most thunderstorms of all the states. And it makes sense because something like 90% of the state of Florida is within 30 miles of either the Gulf of Mexico or the Atlantic. So it's constantly in the presence of these maritime tropical air masses, especially during the summer, that bring all that moisture and rain inland, and it creates an environment where thunderstorms form very easily. And the same thing happens here in Louisiana. It's why from the late spring well into the early fall we get thunderstorms just about every day, because that air mass brings that moisture inward and it reaches here and the conditions form for thunderstorms to happen here. So there are three major types of thunderstorms. And the most important factors that determine which type of thunderstorm can form are the atmospheric humidity and the amount of wind shear in that system. Wind shear is defined as changes in wind speed and direction with altitude within the cloud system. So weaker thunderstorm systems can't tolerate much wind shear at all, but much bigger, more powerful, and consolidated thunderstorm systems can tolerate a much higher amount of wind shear, like hurricanes and strong tornado systems, as we'll talk about later. So our first thunderstorm type is simply called the single cell thunderstorm. These are relatively mild and short-lived thunderstorms that we experience all the time here in South Louisiana during the summer. Single cell thunderstorms form within a maritime tropical air mass where the wind shear is weak. Remember, it's a very small storm system, so if the wind shear is too high, it's going to break up the clouds before it can form properly. So there has to be a weak amount of wind shear for a single cell thunderstorm to form. These generally develop in the late afternoon, and they typically have a very predictable, stable sequence of growth, maturation, and dissipation. That sequence has 3 steps. First, it forms within that maritime tropical air mass into an organized cumulus cloud. Remember, we talked about those in the second unit. So first it forms a cumulus cloud, and then, because of a strong updraft, the second step is it matures into a full organized storm system. There's lots of condensation and evaporation going on within that cloud, and that's when it starts to really rain heavily. And the third and final stage is once it gets cut off from its moisture and its fuel source, it'll quickly dissipate and evaporate. So these storms happen all the time during the summer, and they're very difficult for meteorologists to predict exactly where they're going to happen. We can predict if the conditions are going to be right for them to form, but it's very difficult to analyze exactly where they're going to happen over the land. So that's why sometimes during the summer, it'll say like you have a 10% chance of rain in your area and you still get hit by a thunderstorm. Well, that was one of these. It's very difficult to predict where they're going to happen. They generally last only an hour or two because they're not very big, they're not very organized, they don't have the staying power that a much bigger storm system does, that we'll talk about with the next two types. Our second thunderstorm type is called the multi-cell thunderstorm. So as the name implies, these are multiple thunderstorm cells that have merged and grouped together. It's much more powerful and organized than our single cell thunderstorm is. These form under conditions of moderate wind shear, so they can't tolerate a very high amount of wind shear like the really big storm systems can, but they're not going to break apart under a moderate amount of wind shear like a single cell thunderstorm will. So these form along fronts rather than within an air mass like the single cell thunderstorm does. So as fronts move along over the land, they'll often drag these storms along with them, and they move in very predictable fashions. They're much easier for meteorologists to predict whether rain is going to happen in a particular spot if we can track where that front is moving and whether or not the conditions are going to be right for a thunderstorm to form in that spot. So these are much more easy to predict than the single cell storms are. Multi-cell thunderstorms are arranged either in clusters or what we call squall lines. A squall line is a line of multi-cell thunderstorm systems that typically form along a cold front on a mid-latitude cyclone. So a squall line is a line of multi-cell thunderstorm cells that typically forms along a cold front of a mid-latitude cyclone. These multi-cell thunderstorms will often produce severe weather. And how we distinguish a severe thunderstorm is that it produces either hail 1 inch or greater in diameter, if it spawns a tornado, or if the wind gusts are 58 miles per hour or greater. So there are kind of three thresholds that we use to distinguish a severe thunderstorm from a non-severe thunderstorm. And we'll often see these multi-cell thunderstorms spawn severe thunderstorms wherever they move over the land. These tend to spawn tornadoes and all kinds of really nasty weather conditions like hail. Single cell thunderstorms are not organized and powerful enough to cause severe weather, but these multi-cell thunderstorm systems are. So if you ever look at your radar and see a big line of thunderstorms coming your way, that's probably what this is. These can last for many hours or even a couple days, depending on how large and how powerful that front is that's bringing these things along. And that'll bring us to our third thunderstorm type, which is by far the scariest one, called supercell thunderstorms. Supercell thunderstorms form over land where there is humid air and strong wind shear. These contain a special type of rotating cylindrical updraft called a mesocyclone. These produce almost all powerful tornadoes that will spawn out of the cloud from that mesocyclone structure. So strong wind shear will tear most cloud systems apart, but in the case of a supercell thunderstorm, it's big enough to not only withstand the strong wind shear, but the strong wind shear will actually spawn things like tornadoes from that cloud. Page 168 of your textbook has a really good set of images as to what that mesocyclone, that rotating cylindrical updraft, looks like, and it's really easy to visualize how it spawns tornadoes. Now, these type of clouds are very big and ominous. You could usually see them from very far away, but what you can't always see is the actual tornado itself, if there is one, Only about 30% of these type of storm systems actually spawn tornadoes, but if it's obscured by a very thick layer of clouds, which often is the case where we are in South Louisiana, you might not actually be able to see the tornado until it's right on top of you. So a lot of storm chasers actually refuse to even patrol our part of the country because it's just too dangerous for them. Whereas in the Great Plains, the air is much less humid and you're much more likely to be able to see the tornado from further away as it touches the ground than you are here. So to recap our three types of thunderstorms, we have the single cell thunderstorms, which are relatively small and weak. They last only about a couple hours at the most, and they form within maritime tropical air masses during the summer usually. Second, we have multi-cell thunderstorm systems, which are much more organized, and they move along cold fronts and squall lines and can deliver sustained rain over a given spot for many, many hours. And last, we have the supercell thunderstorm system, which has that rotating mesocyclone within it, and these spawn almost all of the powerful tornadoes that you might see on the news that really devastate an area. They come from this type of storm system. Now we'll talk about some of the things that often accompany these thunderstorms. First, we have lightning. Lightning is defined as the electrical discharge that is produced by thunderstorms, and it'll always follow the channel of least resistance. It wants to transfer that energy in the most efficient way possible, so it's always going to choose the easiest, most efficient route to do that. So most lightning is either cloud to cloud, so an electrical discharge between two clouds, or even within a single cloud system. Only about 25% of lightning actually hits the ground. About 75% of it just stays in the sky. It never actually touches the ground. As for the cause of lightning, a bolt of lightning is formed when two oppositely charged regions develop an electrical connection. So when lightning strikes the ground, that's because the Earth's surface has a negative charge and the upper atmosphere where the lightning forms has a positive charge. So to balance out the two charges and achieve equilibrium, a bolt of lightning will strike the ground if the conditions are right. And that separation of charges will also cause lightning within a cloud or between two clouds. So an electrical connection is formed, and the way the charge is balanced again is a transfer of energy through a bolt of lightning. So thunder, which always follows lightning, is the acoustic shock wave produced when lightning rapidly heats and expands the air around it. So a bolt of lightning carries so much energy with it that when it reaches its target, the response is that an acoustic shock wave will reverberate outwards from where it connects as the lightning rapidly expands and heats the air around it. And if you happen to be very close to the area where that lightning connects, it's going to be a very loud, very quick acoustic shock wave. Whereas if you're further away, it's going to take much longer for the thunder shock wave to reach you. You might not even hear it at all if you're really, really far away, many, many miles. But if you're very close to the lightning, you're going to see the lightning strike and almost immediately experience the thunder shock wave because it's traveling near the speed of sound. So we'll wrap up this video by going into more detail about tornadoes. A tornado is a violently rotating column of air that descends from a cumulonimbus cloud and actually touches the ground. If it doesn't touch the ground, it's not defined as a tornado. It has to actually have the funnel make contact with the ground, even if it's only for a few seconds, to be considered a tornado. And we have a special name for the type of cumulonimbus cloud that tornadoes spawn from. We call it a wall cloud because these clouds are often very, very wide and very, very tall. They almost look like a wall when you're close to them. They're very large, intimidating clouds. And if that funnel cloud created by the wind shear and the mesocyclone, if it actually touches the ground, we call that a tornado. Sometimes you'll see these funnel clouds kind of pop out of the cloud, they'll spin around for a little while, and they get sucked back into the cloud before they actually touch the ground. We don't consider that a tornado. It has to actually touch the ground to be considered a tornado. So tornadoes can form within thunderstorms. They can form along cold fronts like the squall lines we talked about earlier with the multi-cell thunderstorms, and they could also form from hurricanes. Sometimes really powerful hurricanes like Hurricane Andrew back in the 90s will spawn dozens or even hundreds of these little baby tornadoes everywhere because they're carrying so much energy and violent wind shear with them as they move over the surface. They'll spawn tornadoes. Often not very powerful ones, but they'll spawn a huge quantity of relatively small, weaker tornadoes. So we rank and classify tornadoes based on a scale called the Enhanced Fujita Scale, or the EF scale for short. So the EF scale classifies tornadoes by estimating the damage that they've done to the landscape and human property. And it's not a perfect system, but because tornadoes are so powerful and dangerous, and they withstand any instruments that we could put into them, we can't actually classify them based on the damage they're doing as they do it live. We have to kind of go afterwards and analyze the damage that they've done to the landscape after the tornado has already passed. So it leads to some imperfect conclusions sometimes, but it's still a pretty good way to classify the damage that they've done. So the EF scale runs from the EF 0, which is basically no significant damage to the landscape, all the way up to the EF 5, which is just devastating, catastrophic damage to a human structure that basically leaves nothing left but the concrete foundations, just devastating wind speeds. Now, because it's classified on damage rather than the actual wind speeds of the tornado, that does hypothetically mean a very powerful tornado could land in the middle of a cornfield and really do no damage. That would technically be an EF 0, but for the most part, those powerful tornadoes are going to land in places and move to places where they do significant damage to some type of structure that we can quantify, and that would be a much stronger tornado like an EF 4 or an EF 5. Thankfully, about 80% of the tornadoes in the United States are either EF 0s or EF 1 tornadoes that do little to no damage to the landscape. Only about 1% of all the tornadoes in the U.S. are EF 4s and EF 5s that do devastating amounts of damage. However, that small 1% of tornadoes causes about 2/3 of the damage and deaths from tornadoes nationwide. So there may not be too many of them, but when they do happen, like in Tennessee a couple of months ago or in Mississippi last week, they tend to cause very devastating amounts of damage and often high death tolls, especially if they happen in the middle of the night and people can't prepare for them as well. So the EF 5 tornado is considered the largest and most locally intense storm on the planet. Hurricanes might be bigger and impact a much larger area, but tornadoes have a much more powerful concentration of wind speed on the locations where they move over. And often these wind speeds can exceed 200 miles per hour in an EF 5, which is just an incredible amount of wind that's going to rip apart almost anything that it encounters. Even the most well-built structures are generally not going to stand up to wind speeds that high. As for the geography of where tornadoes happen, the United States has the most frequent and the strongest tornadoes of any country in the world. They do happen in some other countries, but with nowhere near the number and the severity of the tornadoes that we get here in the United States. And of all the American states, Florida has the most tornadoes, not necessarily the most powerful ones, but they have the most tornadoes because of that air mass factor we talked about earlier, where Florida is just very, very close to the ocean, and it's very easy for storm systems that spawn tornadoes to form in Florida. The most active period for tornadoes is from April to July. So right now in early May, we're in the middle of tornado season, basically. Now, we don't have to worry about tornadoes too much in South Louisiana. We don't get many of them, and the ones we do get tend to be very weak. But as we go further north, tornadoes are a significant risk because you have these warm, humid maritime tropical air masses that interact with the dry, colder air masses that move from the north. And as those two air masses meet, you can generate some very, very powerful thunderstorms that will spawn tornadoes. So the area of our country that gets the most significant, the largest, most devastating tornadoes is called Tornado Alley. And it's in the Great Plains region of our country, which runs roughly from North Texas around Dallas northward into about South Dakota. So states like Oklahoma gets hit really hard by tornadoes every year. Kansas, Nebraska, Iowa, the Dakotas, they get lots of really devastating tornadoes every year because of the dynamics of these air masses during the late spring and early summer. They're moving over North America and meeting in this area and spawning some very large, very devastating tornadoes. So most of the time when you look on the news and see an EF4 or EF5 tornado is formed, it's generally going to be in this area of the country called Tornado Alley. And tornadoes are such a common thing there that a lot of residences have built-in tornado shelters where people can go into like a strong basement area that the tornado can't damage them there. So even if their houses get destroyed, they can at least hide themselves and their pets and a few important possessions in that storm shelter that the tornado can't destroy. And they've also designed their buildings to withstand some of the weaker tornadoes, kind of like how we've tried to make our buildings hurricane-proof in South Louisiana. So our final topic in this video is about tornado safety. So a tornado watch is an alert issued by the National Weather Service when conditions in your area are favorable for a tornadic thunderstorm to form. So that does not mean that a tornado has been seen or confirmed to land on the ground yet. They'll just send you this alert when conditions are favorable for a tornado to form. So the National Weather Service is looking at the patterns of the air mass, and they've determined that in your area, a tornadic cloud is possible to form from a certain time frame. So they'll send you a tornado watch on your phone. That doesn't mean one's landed yet. It just means that conditions are favorable when they send you a tornado watch. Now with a tornado warning, that means the National Weather Service has confirmed that a tornado has actually hit the ground. Either it's been called in from a local that has seen it, or they've noticed on the radar what we call a Doppler hook echo signature. So when that tornado funnel cloud spawns out from the larger cloud and actually hits the ground, on radar it looks like a sort of fish hook based on the way that the air is spinning. So when meteorologists see that hook echo signature, they know that a tornado has actually hit the ground in that location, and they'll send out a tornado warning alert. So again, tornado watch just means that conditions are favorable. They haven't seen one yet. A tornado warning means a tornado has actually been confirmed in that area, and everyone near that area needs to seek shelter immediately.